everyone. We will talk about AR-based BIM visualization by Microsoft HoloLens.
The construction industry has been transformed by BIM, which enables collaborative project plan, design, and management through digital models. However, traditional reliance on 2D screens in BIM systems limits spatial understanding and visualization, potentially leading to errors due to discrepancies between digital models and physical sites. Although BIM software can represent structure in 3D, flat screen restricted immersive depth and interactive capabilities essential for accurate spatial perception. This has created a demand for advanced 3D visualization tools. AR technologies such as Microsoft HoloLens have emerged to bridge the gap between digital models and reality. By overlaying BIM data onto physical space, AR enhances spatial understanding for architects, engineers, and construction managers. The integration provides a more immersive experience, aiding informed decision making and reducing errors from misinterpreting 2D plans. Incorporating AR into BIM workflow offers improved spatial comprehension, decision support, and enhanced collaboration, leading to a more accurate and efficient construction process. Real-time design examination, issue identification, and collaborative problem-solving streamline decision-making, reduce rework costs, and boost efficiency without sacrificing accuracy. Consequently, AR integration is becoming increasingly suitable for the construction sector. Traditional 3D visualization on 2D screen hinders users' ability to grasp depth and spatial relationship accuracy. Immersive 3D visualization tools and AI applications address this limitation, offering intuitive ways to explore and understand complex construction models. So HoloLens enhances 3D visualization by overlaying holographic models onto real-world space. It provides mixed reality experience that enable interactive engagement with BIM data. So benefits and features of HoloLens in BIM. So firstly, immersive experience and error reduction, collaboration enhancement, and future integration. For a practical experience with Microsoft HoloLens, it conducts several BIM-focused sessions at the Industrial Center and investigates spatial mapping and gesture-based control system. And finally, it is valuable for integrating HoloLens into construction workflow, particularly benefit for complex projects requiring enhanced spatial visualization. For AR technology, there are benefits but challenges such as the learning curve for new users and limitation in viewing large models emphasize the importance of user training. Overcoming these challenges is crucial to fully leverage HoloLens capability in construction projects, paving the way for immersive interactive environment that bridge the gap between digital design and physical reality.
Then let me introduce part 4. In this part, we explored 5 typical applications. As for the first 3 applications, we conducted 3 experiments in our 3 trials, in which we obtained relevant data to support the applications of HoloLens. As for remaining 2 applications, we collected corresponding literature to support them. From application 1 to 3, we can see that many quantitative data are obtained in our experiments, such as 25% reduction in the time and 10% increase in the detection of discrepancies, which we will elaborate in part 5. As for application 4, using HoloLens allows workers to identify the precise position and orientation of each component within the overall context of the building. Such precise guidance helps minimize errors, decrease rework, and enhance overall efficiency. As for application 5, by overlaying safety data onto the real-world perspective, workers can gain better situation awareness and the workplace accident risk will be lower. In part 5, I will explain the processes of our 3 experiments in detail to assess the feasibility. In experiment 1, a BIM model of a small office building section was prepared. 3 team members respectively served as architecture, structural engineer, and contractor to have a briefing training session to discuss design review process. Then the HoloLens was set up and the BIM model was loaded onto each device. Each one was assigned a specific floor plan to review. In data collection, the review was timed using a stopwatch, and we used HoloLens annotation tools to mark clashes. In post-trial analysis, a comparison was made with review time and clashes identified using traditional 2D drawings. This experiment simulated a real-world construction site using a constructed physical model and the corresponding BIM model. Team members used HoloLens to overlay the BIM onto the physical model. Comparing the physical progress to the design, the goal was to measure improvements in discrepancy detection. Processes similar to last experiment. There are preparation work, task process, data collection, and post-trial analysis, and the results show a 10% increase in the early detection of discrepancies. This experiment evaluated HoloLens' impact on stakeholder understanding. Two simulated stakeholders, one with construction background, one without, were selected to represent typical client profiles. Then stakeholders independently explored the model using HoloLens in a quiet room, with team members available for immediate questions. After the trial, each stakeholder completed a questionnaire comprising questions on understanding, ease of use, and visual clarity, alongside open-ended questions for detailed feedback. From above three experiments, we obtained corresponding results which quantitate the effectiveness of using HoloLens in typical applications as well as their feasibility.
For part 6, we will talk about the benefits and challenges. About the advantages of HoloLens, the first is enhanced spatial understanding. It provides immersive 3D visualization of BIM models, allowing stakeholders to work through digital models. The second is the collaborative design review. It reduces design review time by 25%, and the third is the real-time monitoring, overlaying BIM data on physical structures and reduce the discrepancies. HoloLens provides a 3D overlay that helps users comprehend the spatial configurations better, and this reduces the potential for design errors. And the 15% improvement in detecting design conflicts through increased spatial awareness. It facilitates the real-time collaboration by allowing multiple stakeholders to interact with the 3D model together in the physical environment, and 25% reduction in design review time compared to the conventional 2D methods. The real-time proactive monitoring reduces the costly rework and aligns construction with digital models, and 30% improvement in early discrepancy detection, enhancing quality control. About the challenges of implementing HoloLens, the first is the narrow field of view. Users may need to reposition or zoom in frequently to view the large BIM models. The second is interoperability issues. When exporting and importing BIM data to and from HoloLens often requires third-party plugins. And the last is about the learning curve. The gesture-based controls require the training. Initial sessions show that team members need practice. HoloLens' narrow field of view can hinder user experience, especially with large BIM models, and the compatibility with existing BIM software is limited, often requiring third-party plugins, and the initial sessions indicated a need for further familiarization with this interaction among team members, slowing adoption. The last part is about the suggestions for better use of AR-based BIM visualization. For suggestions for better use, the first is about the workflow optimization, adapt workflows to include AR early in design for conflict resolution, and then it's about improve the interoperability, use open source formats and standardize the data models. And third is advanced training programs, conduct scenario-based workshops to familiarize users with gesture controls, and the last is about structured feedback mechanisms, collect and analyze feedback to refine the AR/BIM workflows. Thank you for your time, and here is our reference list.